So you think you can live up to those kinds of expectations?
I plan on exceeding those.
Oh, good. All right. So I thought we'd spend a little time reviewing. Let's start off. Here's the most modern periodic table I could find. And you can see over here, it's got Tennesseum, element 117, and the latest one, I think 118 was discovered before 117. As I remember, 118, the guy who claimed discovery didn't really discover it and faked the data. But in physics especially, people like to have another experiment that gets to the same answer by a different path before people really want to trust the first experiment. And that's how they caught him, when they realized that he could not possibly have had the data that he had.
Wow. Didn't it only exist for like a nanosecond or something? When they created
the Tennesseum, they made 7 atoms, I think, and then saw them all decay.
Wow.
And I was hoping to get the guy who was part of the discovery team, he's up at Oak Ridge, to come and talk about it, because how they do that is they put those, they spread out the material they think may have the element in it, and then they slap a detector on it. And so you have a 50% chance of seeing any kind of interaction or decay process from a decaying atom that way, because it either goes up into your detector or it goes down away from your detector. And so they get a lot of data from very few events that way, but it's enough for them to figure out what they've looked at. Anyway, the point of this is, when this periodic table was first created, they didn't arrange it by the numbers in the upper left-hand corner. They arranged them by the mass of the elements. And that was all compared to, I think, at hydrogen at the time, but now we compare everything to carbon-12 for the mass number. And it wasn't until Moseley came along and looked at the X-rays from these different elements and showed that there was a characteristic X-ray that the Bohr model could be used to explain, and that by looking at the periodicity that each element, when you changed, these numbers up here seem to correspond to the number of positive charges in the nucleus. And so since they knew that hydrogen had 1, that meant all those 1 increments meant that you were getting 1 more proton added to each element. And that was the deciding factor for the arrangement of the periodic table, and not necessarily the masses. The masses do get you in the ballpark, but they don't explain the chemistry without a few switches. So it was interpreting the decay, decay of an excited state. Moseley had heard about somebody else's work where they were using high energy electrons to create X-rays. And so he started putting a target there for the electrons to hit that was uh, allowed these characteristic transitions to take place. And this structure for atoms was due to Bohr, right? These were the n equals to 1, the n equals to 2, the n equals to 3. And it was these transitions that Moseley correlated with the X-ray peaks that he was finding. And he had to have that model in order to be able to, excuse me, to be able to show that the energies that he got depended upon the square of the charge, and that charge, when you took the square root, was that integer. So here's the kind of data he was dealing with. It's pretty high resolution data. It's an ugly graph, but and he did it not with the energy, but with the frequency. Well, actually, went over the wavelength is what he was dealing with. So it was what was predicted by Bohr's model, and it gave people the idea that there were these protons. Now, of course, it was Rutherford that made the discovery that there was a nucleus at all. So they were working, there was no Bohr model until there was a nucleus. So the Rutherford scattering is what really proved that there was this massive thing in the center of an atom that was very small. And he went about determining the sizes by looking at what energy they had to get before you stop seeing Rutherford scattering. Rutherford scattering, the projectile does not touch the nucleus. But if you get high enough energy and it does touch the nucleus, then it doesn't Rutherford scatter anymore. And so he would look at the angle at which it quit Rutherford scattering, and he could deduce the size of the nucleus. And so he had this empirical equation for alpha particles coming in and scattering off of a nucleus. And that's the radius was 1.2 femtometers times the cube root of the number of protons and neutrons. Now, at the time he was doing it, the number of protons and the proton mass did not give you the mass of the atom. So they assumed that there were twice as many protons, but there must be an electron with one of the protons so that it was neutral. So they were already speculating there was a neutral particle. And it was Chadwick who came along and did an experiment that created the neutron and allowed him to measure its properties. And so the nucleus then would be like this model of a neon 22 nucleus. These are your neutrons and these are your protons. And the volume of this thing is just equal to the volume of one of the balls times the number of balls. So if the volume is proportional to the number of balls, then the radius must be proportional to the cube root of the number of balls. And we need that idea. By the way, this is about what a neon nucleus is supposed to look like. Sort of elongated. It's not spherical at all. So here's a semi-empirical mass equation. The idea is that you can predict the mass from just knowing the number of protons, Z here, and the number of nucleons, the protons plus neutrons here. So although we call A the atomic mass, it's really just a counter, the number of protons and neutrons. The actual mass is a much more precise number. And these things are measured by taking the atoms and accelerating them and leaving them ionized and having them go through a magnet. And the radius of curvature depends upon the charge, and it depends upon the mass of the particle. So you can put these things through big magnets and measure the position at which they came out very precisely. And you can measure these masses to 7 or 8 significant digits. By the way, I'll put this PowerPoint in the folder so that you can have access to all this stuff.
Cool.
I'm going to try to have it in ahead of time, but I'm not efficient yet. Well, you had and should still have this spreadsheet. Has everybody still got a copy of this, or do I need to send you a new one?
I think we should. I'll check.
We all should have.
I'll put a slightly newer copy in the Dropbox folder. So this is the same formula that you just saw. And this is in units of AMU. And so the mass of any nucleus is just let's say the mass of any atom, because this equation calculates the mass with the electrons with it. So we're using here the mass of the hydrogen atom, which is also the number of protons. So we multiply by the number of protons, and that brings the electrons along with it. This, A minus Z, is the number of neutrons, and this is the mass of the neutrons. So these first two terms represent the sum of the masses of the electrons, the protons, and the neutrons in whatever atom you're looking at. But then we've got to subtract off the binding energy, because when we put them together, their mass decreases. They give off energy so that they're bound together. And you've got to give that energy back in order to pull them apart. So this is called the liquid drop model. We mentioned that before. But the idea here is that this term, that every particle interacts with every other particle, and you have an infinite number of particles, and every particle has the same interaction that every other particle does. And so whatever that binding energy is, you multiply by the number of particles and you subtract that off, and that's your binding energy correction. So that's what we call the nuclear force. But no nucleus is infinite, and you've got to subtract off the particles at the surface. They only get to bond to half of the particles, so their binding energy is different. You've subtracted off too much, so you have to add back a little mass. And so whatever that number is, this is a semi-empirical, so it means it's fit to real data. The surface is going to be an r squared, 4 pi r squared. So you throw the 4 pi into that A2 term right here. And this is a to the 2/3, because remember, r is a to the 1/3. So r squared will be a to the 2/3. And so that's what this term is. So this is, everything's got a same binding energy, and now we're correcting for the size of the nucleus by having a surface area effect. Then we've got to subtract off something related to the Coulombic repulsion. This is just the nuclear force attraction. This nuclear force repulsion is going to have to be accounted for. Now, you've got Z protons, so one proton interacts with Z minus 1 protons. But then you've got Z of those protons. So the total interaction is the sum of all the interactions. So it's the first proton interacting with Z minus 1, the second one interacting with Z minus 1, and so on. And so when you're done, you've got Z times Z minus 1. Well, no reason to make it hard on ourselves. We just made it Z squared instead of Z times Z minus 1. You'll see some people get very upset and they'll put that in there. But this is the preferred way to go about it. And you figure that any little bit by leaving off that minus 1 can be absorbed in the A3. So Coulomb's, the electrostatic potential is the charge squared over the distance. So here's the charge squared. Wrong one. Here's the charge squared. And here is the distance, 1 over the distance. The force is 1 over the distance squared, but this is the potential energy, so it's 1 over the distance. So that's that correction. And then there's this correction right here. And this one has to do with asymmetry. If this disappears on me occasionally. This term right here, let me go over to the I'm gonna go over to the whiteboard for a minute. And so we had A minus 2Z over A times a coefficient. And it's the A minus 2Z. So A minus Z is the number of neutrons. And so A minus 2Z is N minus Z. So it's the difference in the number of neutrons and protons. That's what this A minus 2Z is. We're just not using the neutron number in there.
So that A minus 2Z over A was what?
It represents the asymmetry term. So if you've got equal number of protons and neutrons, there's no change in the binding. But the neutrons and protons don't really interact exactly the same. And because of that, you've got to have this asymmetry term. So when A minus 2Z is not 0, it means you've got a different number of protons than neutrons. And it doesn't matter if you've got more protons or more neutrons. That term is squared, so it's just how far from equality are you. And the A term, it takes a little bit of explaining to do that. If you want to read about it, Wikipedia for the Weizsäcker mass equation will give you a good explanation of that A right there. All right, so that's programmed in up here. Now there's one other term that has to be added, and that's has to do with the number of protons and number of neutrons. Not a subtraction. It's whether you've got even numbers or even odd numbers of them. So the even you add a term, the odd you subtract some, and the even odd don't do anything with it. So if I've got oxygen, how many protons in oxygen?
Hey,
What's up, David?
sorry.
How many protons in oxygen?
8.
8.
Yeah,
How many neutrons then?
8.
Yeah, it's mass 16. So it's an even. Nitrogen is mass 14. How many neutrons and how many protons?
7.
7 protons.
7, right?
Yes.
Let's see. Let's go to calcium. Wrong thing to do. Calcium.
Okay. 20 protons, I guess.
There's a mass 28 and there's a mass 20 that are both stable. So how many neutrons do you have in each case?
Let's see each.
This is painfully slow.
20
So-
and 28.
If you've got mass 48, you've got 28 neutrons. Mass 40, you've got 20 neutrons. But they're both even.
Yeah.
I'm trying to find one here that's even odd. Oh, let's see. Fluorine, right here. It's mass 19. How many neutrons does it have?
10.
10. So that's an even odd. Even protons, odd neutrons. So that you have to add in. I said you have to do it by hand, but you can actually program this in as a term with a little bit of clever Excel work. You ought to try that. And I think the last day of class, or the next to last day of class, we calculated all the different proton numbers that gave us an atomic weight of 64, and we calculated the the masses, and we got a parabola for that. Do you remember that?
Yeah.
Okay. And we talked about the meaning of that parabola. What was the meaning of that parabola?
It showed
Stable point. Most stable isotope.
Yeah. So if I go back to this equation, which is a nice compilation of the that mass equation we had a moment ago, and here's that even, odd term over here. This view allows you to think about this, for instance, the stability. If we fix an A value, this term has no. This term just has a number. Is just a number now. That term's just a number times z, and this is just a number times z squared, and that's just a number. So what we have are two numbers, the first and the last one that depends upon z and one that depends upon z squared. And I don't know if you guys have had much of this math, but that's the equation for a parabola. So for any capital A value, you will get a parabola for the mass as a function of z. And that means there's always going to be a minimum mass and there's always going to be a stable mass. But how do you go about finding the stable mass?
Graph it.
Let's do it analytically. How could we find it from this?
We find the minimum value.
Yeah.
Take the derivative and set it equal to 0.
Take the derivative of the mass with respect to
A? Or
I
Z?
think it's z, isn't it? That's what you want to think about the parabola. And that's A is constant and Z is the variable. And so if you take the derivative of the mass with respect to Z and set it equals to 0, you're going to find the Z that makes that happen. And as a matter of fact, if you do that, you'll have a relationship between A and Z that allows you to predict the stable mass for a particular atomic number. So I'd like you to do that. And let's see what you get. You got it?
Just with respect to G, right?
0 and then 1, 95.58.
I got to stop doing this. It'll take me half an hour to get this written out. Yeah. So you get this term and then 2 times this term times Z.
Yeah.
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 Not that.
Okay, so that means you can take this over to the other side, put Z squared over there, and solve for A.
So,
And what you have then is a relationship between A and Z. So you could be able to predict, given a particular Z, what the A value is that goes with it. And so here's a graph with such a result on it. The blue dots here are from the back of your textbook, where they've got a table of constant or stable isotopes. And this black line represents the equation that you're generating right now. Now, the equation is really, it's a fit to the data. So it's supposed to look this good. This is the data they use to get the fit. But it averages out. So when you're looking at small values, you want to know exactly the mass of boron 10. It gets pretty good, 3-digit, 4-digit accuracy, but that may not be good enough for what you want to use it for. Now, the differences between two masses are better than the actual calculation of the mass themselves. But when you really want to look at small systematic differences, you want to know how much the mass of a nucleus is changing as you take one neutron after another out of it. It's not going to give you a good result. It'll give you an okay result. But what you may be looking for, you might not see. And that is evidence for the shell effect. But here's what it's really good for. This is called the alpha drip line. And for all the elements above this red line, it is possible, energetically possible, for those masses to alpha decay. So when they alpha decay, you'll get positive energy released. So it can happen. You don't have to provide energy. Below this line, any masses, and over this red line, actually, I should have extended it further, comes over and is above all these. These cannot alpha decay unless you bring energy into the system somehow. So there are proton dip lines and neutron dip lines and all of that. But that's what that equation is good for explaining. If you want to ask, is there a symmetric fission split line? There is. And you can find out what elements can possibly symmetrically fission. Now, going back to those parabolas, you've got an odd number of A. It ends up that last term may not come into play. And so you'll get one element that's stable right here. But when you have an even number of A's, you have the two correction terms that come into play. Because the even, one will be odd, odd, then it'll be even, even, then it'll be odd, odd, then it'll be even, even, then it'll be odd, odd. And so you're adding and subtracting those numbers. So instead of falling in one parabola, the even odd and the odd odd switch, and they split apart, and you get two parabolas. And so in this case, it's possible to have two stable elements. They're both the lowest on the low parabola, but they can't beta decay to each other because they're separated by two atomic numbers. And the one in the middle is up here. And so this happens especially with the heavier isotopes. You get this large separation between the two parabolas. You'll see that with that equation, but you'll also see it with the real data. So here's a summary of what we were doing. We were taking the total mass, the protons and neutrons, and then subtracting off the volume effect. And that's a constant effect. The surface correction to the volume, though, changes, and it becomes less. So this corresponds to this distance right here corresponds at any particular atomic mass to how much surface energy corrections there is. For the small ones, you get a bigger proportion of the surface because there's not much volume for all the surface. But when the things get large, the surface isn't increasing that fast compared to the volume, and the surface energy correction becomes less of the total. But the Coulombic repulsion becomes bigger the more protons you get, because proton number goes up with the mass number. And then the asymmetry goes constantly upwards because you're getting more and more neutrons than protons in a stable nucleus. And this shows you sort of the relative contributions to those terms that were subtracted off in the mass equation. All right, I'm going to get out of this for a minute. Here's the Weizsäcker equation. I wanted to get to this. So this was the other chart. Can you all see that?
No.
Not yet.
Not yet. Okay. Now you can see it.
Mm-hmm.
Yeah.
Yeah, now we can see it.
All right. There are $2,500 entries here, or different isotopes.
Wait, somebody did that for a work study?
People did for work.
Oh my gosh. Wow.
Here's the atomic number, here's the neutron number, here's the atomic mass, here's the lifetime, and here is the actual mass. And this is where the work went in, because in the tables, they don't give this to you directly. You have to calculate it. And here's the natural abundance for that particular element. This is other stuff. The spin parity we'll talk about in a minute. And here's the decay mode, the most prominent decay modes. And then there's some of the energies that are involved with it. But if you do a sort, maybe I better not do that. I didn't select the range there. Quit the program when you're done and open it back up. Quit this file. and then you've saved everything. If you do a couple sorts, it's possible that you're going to start losing data. So when you quit it, don't save changes. So if I wanted to do a sort, I would want to include all the data out here. If not, as soon as you've completed the source, it's no longer related. And a lot of times they won't let you undo a sort. So when you sort, select everything. And then whatever you want to sort on, if you wanted to look at all the masses, all the isotopes for atomic number 15, come on. Yeah, see, I already made a mistake. I'm going to sort on the atomic number. And it's done, and you can see, let's go down to atomic number 15. Here we are. And can you all read these numbers on your screen?
Yes.
Yeah.
Okay. So there are all the known isotopes of element 15. Let's see, element 15 is what? Phosphorus. And here's the neutron numbers for all of them. So they go from 12 to 27. And if you were to graph this data as a function of neutron number, you'd have the number of, you'd get a funny looking graph there. Stability has to do with the with this mass as a function of the atomic number, not as a function of the neutron number. So you can generate any comparison of data that you want to by sorting these things properly. So that gives you a lot of power. And that that chart is available to you, so I'm going to quit it since I did that crazy save. And go back here to the PowerPoint. All right. Another property that you have is the spin of the nucleus. And that can be determined by magnetic measurements. There's a number of different ways to get to this. And there's something a little bit different between the nucleus and the atomic electrons. And that is the parity takes the place of the quantum number. And so you have the spin and the parity. We'll get into the parity a little bit later. The spin right now is just the total angular momentum of the nucleus. If I look at atomic number 4, and it has 10 neutrons. So what's atomic number 4 is beryllium. So this is beryllium mass 14. It has no spin. What? If I look at carbon 16, it has no spin. If I look at oxygen 18, it has no spin. If I look at neon 20, it has no spin. If I look at magnesium 22, it has no spin. I forgot to do something with this one. I couldn't find measurement of it, that it's not zero. What do you notice about all these things that have zero spin?
They're even numbers.
They're all even numbers. So the neutrons pair up and the protons pair up, or maybe the neutrons and the protons pair up. So they cancel their spin. But let's take one that's got an even number of neutrons and an odd number of protons. It's got a spin of 1.5, 3 halves, plus 3 halves. Let's take one with 10 neutrons and 5 protons, minus 3 halves. So here I had 1 extra proton, here I have 1 extra proton. I've got even number of neutrons. So I'm betting the neutrons all pair up, and then the difference is the 2 protons. But the 1 proton, apparently, there's more to it than just it being a proton. There's got to be some other angular momentum effect than just its spin, and that's going to be an orbital angular momentum that comes into play. So we looked at even numbers of A's. Here's 6, 10, 16, 16, and the parity in some cases is 0, in some cases isn't. If it's an even number, you could have an odd, and so you get those parity effects, and you can have even, in which case you don't. You always get the even number of pairing. So apparently it's not the neutrons pairing with protons, it's neutrons pairing with neutrons, protons pairing with protons. If I take mirror nuclei, so if I hold the mirror up, the protons change to neutrons, neutrons change to protons. Their spins stay the same. Here, let's see, 11, 10. So here I'm going to add, what did I do there? Never mind. Here's another set of mirrors. And you see that when I switch them, the parity stays the same. So the protons and neutrons seem to, when you have the same numbers of them, they seem to pair and produce angular momentum that are identical. So that angular momentum, just like with electrons, implied that there's got to be some shell structure. And so you start off with that liquid drop infinite number of nucleons, and you can make it infinite by having a harmonic oscillator potential or an infinite potential well. Either one works fine as a starting point. You had the spherical potential, infinite potential well as a problem and a finite version of it too. I don't think many of you took advantage of learning what was there, but that's the starting point for the nucleus. And so when you add a little bit of squaring to the harmonic oscillator by making it look a little bit more like an infinite square well, then you get a splitting of the harmonic oscillator energies. And this isn't a 1D well, this is a 3D well. And in the 3D well, just like in the hydrogen atom, you get orbital angular momentum. And so that's where the S's and P's and D's came in. The S's, how much, what's the quantum number for a orbital angular momentum if it's an S?
1.
0?
Yeah, Jared said 1.
No, I'm muted. My mic's muted. What are you talking about?
Yeah. He was just snorting over there trying to stay awake. P is what?
P is
1.
1.
Yeah, 1. D,
2,
2.
F,
3.
3. And you notice over here is a G. What's G?
Doesn't exist.
4.
Must be 4.
Before. So after F, it goes alphabetically, F, G, H, I, J, K. And they all show up in nuclear physics. So when you take the finite well, infinite well, and make it finite, all the energies shift a little bit lower. And when you round the edges, you get a little bit lower. And then you put in the spin-orbit coupling. That's where the magnetic interactions take place, the charge and magnetism. So you've got a moving charge creating a magnetic field. The other particle has a magnetic moment. You get an orientation. So that's the spin-orbit coupling. And that splits the two P's into 3 halves and 1 halves. So you get another angular momentum popping in there. And that was the J that we had. So this last thing tells you how many different possible particles can be in here. So if the J equals 3 halves, how many particles are there? What are the M sub J values for J?
J would be like 3 halves, 1 half, negative 1 half, negative 3 halves.
Yeah. Yep, that's it.
So are there 4 possible particles then? So you're saying?
There are 4 possible particles.
So can I get an A on my comp?
We'll think about that.
Here we go.
David, it depends. Can you show up on time for the comp?
My bad, Dr. P.
Oh, there you are. You weren't in the picture a minute ago.
No, it must have dropped. I came in slightly late.
Well, I'm not exactly a pro with Zoom yet. Okay, so the interesting thing here is to look at the spacings of the energies. And you notice there's a gap here. 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 Let's look at how many particles. 1 half. How many particles can be in that?
2.
2. And it's going to be 2 protons or 2 neutrons. So the neutrons and protons individually have their own shell structure. Same shell structure, but they fill it independent of each other. So I can have two protons here. So when I have this big gap, that big energy gap in filling, that's kind of like what happens when you fill the electrons in the atoms going across the periodic table. When you get to the end, to the inert gases, you filled up that energy level. And the next energy level, there's a big gap. And that's the next one. So 2 must represent a nucleus with 2 protons. There's a break. That second proton must make it very stable. As a matter of fact, Z equals to 2 is an alpha particle, which is a helium nucleus, which is the most stable nucleus. Then when I start adding more protons, I'll add 4 here, right? 3 halves, 1 half, minus 1 half, minus 3 halves. And I'll have 2 here. So I'll get 4, 6 here. And when all of these are full, I'll have another closed shell. And so that'll be an atomic number of 8. 2 down here and 6 here. And that's your oxygen. It's super stable. Then I come up here, and 5 halves is going to give 5 halves, 3 halves, 1 half, minus 1 half, minus 3 halves, minus 5 halves. So that's 6, 4 here, and 2 here. So that's 6, 10, 12.
I hear Brian.
So you've got a way to predict what are called the magic numbers, and we're not actually done with this chart. There's a few more small things to consider. The magic numbers. Do you know what they are?
Oh, you know. Hold on.
Is it 2, 8?
18's one of that.
Actually, it isn't.
Ah,
So 2, 8, 20, 28, 50, 82,
126.
126, 184. So another thing to do then is to figure out how many particles go in here. And by the way, this is in the Dropbox. You can get it. It goes up further. And find out where the actual magic number breaks are and see how distinct the energy difference is when it gets you there. All right, so we've pretty much used up our time for today. I have no idea where I am. There we go.
There it is.
So here's what I'd like you to do. There were some problems assigned for today. I'd like you to get those done and email them to me. I'd like you to use Tiny Scan. It's a $5 app for your phone. If you take pictures of what you do and you send them to me, you won't be able to email them. They're going to get too big. I couldn't email this 8-page PowerPoint to you because it got too big. I'll use Dropbox for it, but I'd like you to email your stuff to me. So Tiny Scan you take a picture and it improves the color resolution and then makes it 1/10 its normal size. So there won't be any problem emailing those to me. When it comes time for taking tests, we'll do it after hours. We won't try to fit it into the 1-hour lecture block, and we'll use that 1-hour scheduled time for questions and working a few problems before the test. Does that sound okay to you guys?
Scheduled for.
So we'll probably do the tests like at 6 o'clock to 8 o'clock at night.
What's dinner time?
7 to 9 for me.
7 to 9. Okay, we'll do it 7 to 9 then.
Or no, I'm saying that's what it is for me because we're on Central Time. I'm on Eastern Time.
Yeah,
Yeah, Jared's weird like that.
Yeah. So let's not do 7 to 9 Central.
So we'll talk this through, but that's where I think we're headed with this. Also, I'm going to try to make some movies of lectures that you can see beforehand. I thought I would start off this way, but it took long enough for me to figure out how to use Zoom that I didn't get that done, but that's my goal, is to have those so you'll be able to look at them before class. We spend class more on problems and calculations. All right, guys. Good seeing you all.
Yes, sir.
And see you again on Wednesday.
Will, you got a
Hey,
mustache. I didn't know that.
when is our next test?
Let's see. I sent an updated syllabus to you with the schedule on it.
Okay.
Hey, Dr.
Or
P,
an updated schedule, anyway.
I got one question real quick, and it's mainly for seniors because it's about the comp. Can you run through the questions that are on each test one more time? You said there's only 14 now on the first day.
I think that changed. I have no idea what happened, but on the first test, there are 4 mechanics, 4 E&M, 4 modern, 2 on optics, or 2 on waves. I think that's 14 questions.
Yes, sir.
And then on the other one, it's 3 E&M, 3 mechanics, 3 modern, 2 optics, 2 thermo, and 2 astronomy.
Awesome.
And then is the oral part, is that just anything you want to ask us, you ask us, or is there like a method?
Yeah, well, so for instance, you wrote down that the charge of the electron was 1 coulomb, and you did some calculations for the Bohr atom, and you predicted the wavelengths that were just perfect. And we're thinking, how could you get 1 coulomb for the charge and get these wavelengths that are perfect? And so we'll probably say, explain how that happened. And you might,
Good at math.
kick the floor and say, gee, I memorized those answers, and I didn't know how to get them.
And that's a part of the oral.
And we go, okay, you deserve to miss that problem.
Wi-Fi's broken.
Okay, so you model it after what we do on the written part.
So what we're trying to find out is, are you as good as your test score indicates you are?
Probably
Or
worse.
are you really as bad as your test score indicates you are? We're just trying to figure that out. What does it mean? It might mean a half a letter grade, unless you do something spectacular in either direction, and it might be a letter grade change.
Can you not fail us, please?
Yeah.
Wrong attitude. So
Can you pass us, please?
the characteristics of the people that have failed over the years is, first of all, their GPA, their regular GPA, was right at a 2.0. Their physics GPA was only slightly higher, like 2.05. And they didn't study for comps. So
we got them beat, boys.
well, don't be too. You'd like to have a good grade on comps too. So that doesn't mean that people have always performed well. D's are given. So you guys, I don't think any one of you is in trouble of failing comps. What we'd like to see you do is get good grades. And so
I can see that too.
when you work these problems, read all of them first. Take the first 5 minutes and read them. You've got 4 hours. Pick out the ones that you know the best. Work them well. And if you discover, oh my gosh, I worked 5 problems and I didn't have a chance to work 3 more, I'm going to quit working on this one. I know how to work and quickly do some others. You probably just gave up points on the problem you know how to work, and you got no points in the ones you didn't know how to work. So, what's a good score? I mean, 60% is passing, and most people get pretty close to that if they're doing poorly. So getting an A means working 8 problems well on both tests. I'd love to see all of you make A's.
Dr. P, wake up. You dreaming.
I know what the reality is.
So, Dr. Pete, I don't know about the other guys, but Wednesday I was going to take that whatever time I had in the morning before the comp to review, like do some last minute reviewing.
Yes.
So I won't be.
I don't expect any of you in class on Wednesday.
Okay, just double check.
Huge.
But remember, this is a 4-hour exam. Get some sleep. You'll wear down and get really inefficient if you don't have some rest.
Just for like, I know it's like 2 days away, but like, how would you advise? I guess like I don't have any of the old tests or anything, so I've just been doing going through textbooks and problems. Like, is there anything else you would like recommend us doing study wise?
Go over the things you know the best.
All right.
Like,
Remind yourself of all the major laws of physics. You know, Maxwell's equations, definition of the potential, Newton's 4 equations, really 5, but we won't ever ask you about the string. The 4 laws of thermodynamics, Schrodinger's equation, time dependent and independent. Remind yourself what the potential energies are for different situations, so you don't panic and use MGH for everything.
As far as like the oral part goes, like, are you really wanting us to run on a window, or what do you?
No. If you've got an iPad with a whiteboard on it, you can use that because we're going to Zoom, or you can have a sheet of paper, write neatly, and then hold it up and let us see it.
Can you read what I'm saying?
F, don't even show up. That's probably the best way to do it. I mean, if you had a chalkboard or something, if you write on a window, it's going to be impossible to see it. The windows that people write on, you're close to it, but when it's projected like this, we see everything behind it too, and it makes it hard to distinguish what you're writing. I mean, if you had if you wanted to go to Home Depot and buy a piece of cheap countertop, that works great. You know, white countertop with a marker, if you wanted to do it that way. But white paper works just as well.
My mom won't let me leave the house.
yeah.
Let's say like,
Oh yeah, Home Depot is closed. Right?
Home Depot's not closed. It's open.
Nah.
My
Home
state
Depot
is
is
closed.
It's open.
Yeah, Home
They're
Depot's
open.
open. I'd start my shifts back there on Friday night.
are y'all gonna ask us any questions?
For this, in case like household things break and you need to fix them.
You're going to work before the semester's over.
Yeah, I mean it's part time, so and I work nights, so I work like 5-hour shift 3 days a week at night.
Yeah, that's not a real smart thing to be doing.
Ooh.
I'm off Tuesdays and Thursdays, so I work Monday, Wednesday, Friday nights.
Instead of studying.
Well, instead of sleeping.
Yeah. You've got seminars still, and
Yeah, how's that going to work?
So if we already gave our talks, does that like factor into anything out of curiosity?
yes, it does.
Okay.
Thank you. Cool.
But you'll probably give a 20-minute talk anyway, and you'll probably be a whole lot better at it because you did the 1 hour talk.
Cool.
But there are not many weeks left before all that has to come to an end. So you guys need to be putting in some time on that too.
On the oral, would y'all ask us any questions? Like, let's say I don't answer one particular mechanics problem. Would you like ask us about something we didn't even attempt, or?
Sometimes yes. And the reason is some of the problems can be fairly easy, or part of it can be very easy. And so we're wondering, you didn't realize that, you missed out on a chance for a few easy points, or you just didn't have time to look at it. Sometimes that happens, not usually. A lot of times we don't even ask you about the problems on the tests. We ask you something different.
120 volts.
You guys won't, you got
15,
that's
15,
yes,
20
yes.
amps.
Yes, you'll get asked. I have a special circuit that I always bring out for comps, but you guys won't get to see it.
You take some photos. I'm feeling pretty good on my circuits,
Yeah, we're really good.
This one's a mean circuit.
Delta
Okay.
Star, let's go.
The best or whatever.
That's what it sounds like. The oral is. It's like, hey, let's just give him something real hard.
Yeah, so let's just mess with it.
Y'all laugh about it, like watch this.
I got hired at
Yeah,
the university.
Watch how dumb it makes David look.
Watch this. Hey, tell me about this.
Yeah, when I got hired at the University of Connecticut, they had a party for the new physics faculty. And a friend of mine brought out the circuit and said, "Here, explain this to everybody." I mean, it's evil.
So that's
evil
the
aspect.
special
And if
circuit is
you're
just
not under pressure, you can probably sit down and come up with it. But when you're being introduced to all these faculty, one Nobel Prize winner there, by the way,
You're looking at 9 Future right here.
it was not fun. So anyway, yeah, when you guys come back, I'll show it to you.
Okay.
Years from now. All right, guys. Any other questions?
Oh, for advanced lab, do you think we're going to meet the whole time, or what do you want to do today for that?
That'll be just a discussion about how we're going to do things. So
Okay.
for Minju and Brennan, they're going to be they're going to do a LabVIEW project where they can access equipment that's hooked up to a computer and run it remotely.
Okay.
Andrew, we have a Zoom meeting with Dr. Donovan at 3.
Okay.
Yeah, so